There are four fundamental particle interactions. The first is the electromagnetic force. It is responsible for attractive and repulsive forces. It has an unlimited range and is carried by the proton. The second is the strong nuclear force. This is the force that binds quarks together to make baryons such as protons and neutrons. The third is the weak nuclear force. This one changes flavors of one quark into another. It is what makes the deuterium fusion of the Sun possible. The fourth is the gravitational force. It is always attractive and acts from the center of mass of one object to the center of the mass of another. While quarks experience all four of the fundamental forces, leptons only experience three. They don't experience the strong nuclear force. There are 6 different types of quarks and leptons. The 6 quarks are up, down, top, bottom, strange, and charmed. The 6 leptons are electrons, neutrino electron, muon, neutrino muon, tau, and neutrino tau. The basic composition of a proton includes 2 up quarks and 1 down quark. A neutron consists of 1 up quark and 2 down quarks. A particle accelerator is a series of circular tubes, increasing in size, that accelerate particles by using electromagnetic fields. The particles then collide, and the results are recorded for research. The information recorded depends on the detector used, and the purpose of the specific experiment. Detectors have 3 main parts. The first one will track the particles. It will determine the speeds at which the particles are moving, and then a computer can recreate the track and find patterns. The second measures the energy lost when the particles collide. It uses layers of high-density material, such as lead, so that most particles can be stopped, with the exception of muons and neutrinos. The third will identify the particles created in the collision by detecting the radiation emitted from the charged particles. That said, there are different types of detectors that can be used in different scenarios. They can be used to record different information or change the result of the collision. For example, the ATLAS experiment will actually use massive magnets to bend the paths of the particles so that their momenta can be measured. The CERN Large Hadron Collider, or LHC for short, is the world's biggest particle accelerator. It has been made with a collaboration of over 10,000 scientists from over 100 countries and is 27 kilometers in circumference. One of the biggest tasks of the LHC was to confirm the existence of the Higgs particle. They have succeeded with the proof from data released in 2013. 2 of the experiments currently being run at the LHC are the ATLAS and CMS projects. They are both being used to investigate the largest range of physics possible. ATLAS uses a 7,000-ton detector to investigate fundamental forces. This is also one of the experiments used to prove the existence of the Higgs particle. More than 3,000 scientists work on this project. The CMS experiment uses a massive magnet to change the path of particles to alter collisions. The goals of this project are similar to those of the ATLAS experiment. It is looking for the Higgs particle, as well as dark matter and other dimensions. The detector creates a magnetic field 10,000 times that of the Earth. The main discoveries from CERN include the proof of the existence of the Higgs boson particle. There are also numerous other advancements in physics and our knowledge of the universe, such as the discovery of previously unobserved particles. The LHC is currently been shut down due to maintenance and other upgrades. The main upgrades include better connections between series of magnets and repairing vacuum tubes. Canada has invested about $30 million towards research and development, and we have many scientists working on experiments at CERN. We have also made power supplies for the transfer lines, and contributed many other designs.